All right, welcome back. We'll continue with the delicate task of assembling our global matrix vector equations from the specific version that we have of the weak form. And that version of the weak form comes from about the third to last slide of the previous segment. You probably all have it before you in your notes, and I have it here too. So we're going to start working on that. Okay, so we're going to write out the matrix vector weak form in terms of global matrices and vectors. Okay. Okay. For completeness and because there's just one more thing I wanted to say about it, let me just rewrite the weak form that we have. Okay. So we have the following. We have C2 1 E A over H1 minus 1 1 D1 1 D2 1 plus summation E going from 2 to number of elements C1E C2E. Okay, here we have E A over HE 1 minus 1 minus 1 1 D1E D2E equals C21 FA H1 over 2 plus the sum E going from 2 to number of elements C1E C2E in the vector, multiplying the vector, forming a dot product actually with the vector with components FAHE over 2 FAHE over 2. And finally, we have this contribution from the Neumann boundary term. C2 NEL times T times A. Okay, this is what we have. Now, for again notational purposes, I want to state that from the conventional finite element literature, from the traditional finite element literature, that matrix, including the factor in front of the actual matrix, is traditionally called the stiffness, the element stiffness matrix. Okay, we will denote it as K sub E. Okay, where K being a general symbol used for stiffness. Okay, likewise, we can call this sort of a force vector, this sort of vector, the force vector for element E. Okay. All right. So let me just state what these are called. This thing is called the element stiffness matrix. Right, and that is called the element force vector. Now, of course, when we use terms like stiffness and force, this is clearly a residual from the times when the finite element method was thought of chiefly as a technique for structural mechanics. Okay, so we would, but it's convention to continue to sometimes say element stiffness matrix, even if one is doing a problem that has nothing to do with elasticity. Probably it's in the context of heat conduction, it would be more appropriate to call K sub E the element conductivity matrix and Fe as being the element heating vector or something like that. Okay, but this is just terminology that you may see around you in various places. Okay, so this is what we have to do. Now we're going to assemble them, and the process of assembly is the following. Okay, right, this is called finite element assembly, right? So it's often referred to not just as assembly, but as finite element assembly. All right, in order to do this, we recognize that because of the sort of mapping we observed on the last slide of the previous segment, we can write these degrees of freedom that are used to interpolate the weighting function, okay, into a single global vector. We're going to write that single global vector as follows, right? And we're going to write it now using global numbering, because this is what the mapping that we last looked at in the previous segment, this is what that mapping does for us. Okay? So the relevant global degrees of freedom for the weighting function are C2, C3, right? No commas here. C2, C3, so on, up to C, N, E, L, and C, N, E, L plus 1. Okay? Here, I am going to write way over here the corresponding vector of global solution values at the nodes, right? Global nodal solution values. This would be the vector consisting of D1, D2, and these are global, okay? D3, all the way down to D, NEL, and D, N, EL plus 1. What I've done here with this vector on the left-hand side consisting of the C's is collect terms coming like C2E, all the terms coming from C1 and C2 for each element. What I'm doing with this global vector is collect the contributions coming from here and there, recognizing, however, that when we're writing global vectors, we use the global nodal numbering. Okay? Now, the contributions that then come from stiffness terms such as this or the stiffness matrix Ke can be obtained or can be written in a big matrix, okay, which I will sketch out and then fill up. All right. The way we do this now is to observe that there are contributions coming, for instance, C2 multiplies D1 and D2 because of the contributions coming from element 1. Okay? All right? So those would be the contributions EA over H1 with a minus sign here, and EA over H2. Sorry, over H1 again. Okay? So that's what we get from element 1. Let's go to element 2, right? So element 2 would have degrees of freedom, global degrees of freedom, C2 and C3, which would come from C1 with E equals 1 and C1 with E equals 2 and C2 with E equals 2. Okay? And the local to global numbering, the local to global mapping of degree of freedom numbers would confirm for us that the contributions from element 2, as far as the degrees of freedom of the weighting function are concerned, would be C2 and C3. Okay? Now, those contributions come from the entries to this matrix. Okay? Right? So, when we put those together, what we observe is that we get here an additional contribution, and I realize that I'm already running out of room here, so let me just move this over a little. Just move this over to E A over H1 here. Okay? All right. The contributions then coming from element number 2 would be the following. We get minus EA by H1 from element 1 plus EA over H2. Okay? Here we would get minus EA over H2, right? Down here we would get EA over H2, the minus sign, and here we would get EA over H2. Okay? Right? And then we go on to element 3. Element 3 would have C degrees of freedom, C3 and C4. Okay? It would be this one and the other entry which would come just next to it. Okay? Those would map onto the matrix to rows 2 and 3. Okay? As far as degrees of freedom from the displacement are concerned, we would have contributions here coming from, hang on, am I doing this right? Not quite. Okay. We're going to have to back up a little. Okay, so I'm just going to, okay. I'm going to erase this stuff. I'm going to go back to some point, and when okay, all right. Okay. I'm going to go back even more. Sorry, guys. Okay. So we would have to continue again from the point where I wrote out assembly, okay, and then went ahead. Okay. In order to do assembly, we need to assemble the local nodal degrees of freedom into global degrees of freedom. And the way we do this is with recognizing that we get here C2, C3, so on, up to C, N, E, L, C, N, E, L plus 1. We have for the degrees of freedom corresponding to the solution, we have contributions from the global numbering, which are D1, D2, D3, and so on, up to D, N, E, L, D, N, E, L plus 1. So, and here we will write out a matrix in which we will collect the contributions coming from the stiffness matrix, right, from each element. Okay, let's look at what happens with element 1. Okay, Because element 1 has a single contribution as far as the C2 degrees of freedom are concerned, okay, it will fill out only the first row of this matrix, right? As far as the solution degrees of freedom are concerned, it has contributions from D1 and D2, okay? So if we now look at the line above us, what we see is that the contributions that come in are going to be the following. And just for brevity, I'm going to pull EA out of this matrix, okay? All right, so EA is common for all the elements, right? And we are assuming that. Okay, so now what this lets us do is write out the contributions from element 1 as being minus 1 over H1 and 1 over H1. Okay, so minus 1 over H1 will multiply D1, 1 over H1 will multiply D2. Okay, all right. Now then we go into the contributions that come from that sum. Okay, and remember, the very first element that makes a contribution from that sum is element 2. Okay, now recalling our local to global map, we recognize that the contributions that come from the C vector, right, in element 2 are from C2 and C3. This means that we're going to fill out, as far as C2 and C3 are concerned, we're going to be filling out we're going to be again using rows 1 and 2 from this matrix. Okay, but as far as the contributions from the D vector are concerned, the contributions from element 2 are in D2 and D3. So this means that we are going to be getting contributions from columns 2 and 3, okay, or contributions to columns 2 and 3 in this matrix. Okay, so what we get here then are, we have 1 over H1 here. We get a contribution of the form 1 over H2. Over in the next column, we get minus 1 over H2. Okay. In row 2, column 2, we get 1 over H2 with a minus sign. And row 2, column 3, we get 1 over H2. Okay. We go on then to element 3. Element 3 has contributions coming from C3 and C4, which is just next to it. Okay, as far as the D degrees of freedom are concerned, it has contributions coming from D3 and D4, which are next to it. Okay, so it is going to occupy, it's going to provide contributions to our matrix in rows 2 and 3 and columns 3 and 4. Okay, in rows 2 and 3, the contributions are going to be of the form this plus 1 over H3, right? So that's row 2, column 3. Row 2, column 4 is going to be minus 1 over H3. Okay, we will have row 3, column 3, right, which will be minus 1 over H3, and row 3, column 4 is going to be 1 over H3. Okay, this process continues, right? Continues all the way down, okay, until we come to the very last element. The very last element will have a contribution coming from, the very last element and actually the last but one element are the ones that will contribute to the last 2 rows and the last 2 columns of this matrix. Okay? The last but one element is going to contribute a term on the diagonal here, which will be 1 over H N EL minus 1. Okay, right? The very last element will contribute a term here which will be this plus 1 over h n EL. I need a little more room, and I think I can get just a little more room by moving this over a little. Okay, so here we will get a contribution minus 1 over h n EL. Here we get a contribution also from the last element which will be minus 1 over h n EL. And here we get a contribution which is 1 over h n EL. Okay? So these are all the contributions that come from the stiffness matrices, from the individual element stiffness matrices. Okay? What I'm going to do is what I'm going to do is to write this out in sort of operator notation. Now, what is often done here is in the finite element literature is to say that this is the result of assembling over all elements, E equals 1 to NEL. Okay, it's the process of assembling over all elements contributions of the form C1E, C2E times the stiffness matrix times D1E, D2E. Okay, this is just an abstract way of writing it, and what is involved in this operator, in this sort of an operation, is the detailed sort of bookkeeping that we followed by using the nodal and global degree of freedom numbering, right, in order to fill out this matrix.